It's a pleasure to welcome Professor T.V. Ramakrishnan, or TVR as he is called in the true South Indian tradition of initializing people. So TVR is among one of the eminent condensed matter physicists of today. He has made major contributions and major impact in the field of condensed matter physics. So I'll just name a few. He formulated this microscopic theory of freezing, which was the Yusuf Ramakrishnan theory of freezing, when he was in IIT Kanpur in the early 70s. After that, in the late 70s, there was a very famous paper on the field called weak localization, which the community calls the Gang of Four paper, which really opened up the field and started a whole new way of looking at that phenomena. Then in Indian Institute of Science, he was working on phenomena of vortices in high TC superconductors. And he and the group over there formulated a theory of materials which exhibit what is called the colossal magnetoresistance on the manganese. Apart from these physics research contributions, one of his major contributions has been his role in building up an excellent center of condensed matter physics in Indian Institute of Science, Bangalore. And math science has directly benefited from that, in the sense many of our faculty are products of that school or that group. So these contributions have been recognized by both working physicists and the establishment. He is very highly regarded among physicists all over the world. He is a fellow of all the major academies, Indian science academies, as well as the American Physical Society and the fellow of the Royal Society of UK. His many awards include the Bhatnagar Award, the Third World Academy of Sciences Award, and the Padma Shri. So he's still active in research, and he's been thinking about new ways to approach this problem of what we call strongly correlated electrons. And strongly correlated electrons is the topic of what he's going to tell us about today. So let me invite Professor Ramakrishnan to.
Actually, I find it a little hard to believe that this place is 50 years old. But then, that is the chronological age of this place. Somebody once told me that there are three kinds of age: chronological age, physiological age, and psychological age. Of course, you can't do much about chronological age, but this institution, I'm sure, in terms of psychological age, definitely is not 50. And this has played a unique role in theoretical physics and mathematics and theoretical computer science. And I think that the next 50 years of this institute are going to be even greater. So I look forward to it, so long as I'm around. And then maybe whether I'm around or not will play a very great role. I came to know about this institute very long ago. In 1964, I was doing my PhD, and I had gone to a summer school. And to that summer school, two young women had come, Indumati and Bhamati. And we were all in Boulder, Colorado. And from them I learned that there is a new place which is very, very new, which has come up in Madras called the Institute of Mathematical Sciences. And essentially since then I've been a sort of a semi-local person here. So it is very nice to be here. I actually wanted to talk about something else. I might have mentioned this in my email, but when I was asked to talk, then I said, well, I mentioned two topics. One is Vivekananda and modern science, and the other is what you are forced to hear today. You see, the first talk would have interested many more people, but perhaps it would have infuriated the same number of people. This talk probably will interest very few people and probably also will infuriate very few people. So let us see what happens. Okay, so what I would like to talk about is one part of condensed matter physics, which is the subfield of physics in which I have spent most of my life. And this is what may be called quantum condensed matter physics. That is that part of condensed matter physics in which quantum effects are important. Okay, and even there I will talk about one field which is about many electrons which move around, and so the thing in which they move around is a metal, but these many electrons which move around are not quite free to move around, but they are subject to very strong local constraints, which may be described by saying that they like to avoid each other very strongly. So this field, which in more formal language is called the field of strongly correlated electron systems, is what well, I have been interested in, and I would like to bring to your attention, though this is a kind of a technical thing to do, but anyway, that is what I am supposed to do. Now, you see, this is a field in which we don't know what is going on. We, as I have written here, we don't know the language and grammar yet. We can't decipher it yet completely, but it looks like it's a very interesting thing. And if we do understand this, then maybe some old literature will be understood and some new literature will be written in it and so on, and possibly there is some mathematical science there, I don't know. Okay, now I would like to start it, begin from the beginning with the electron. And this story begins sometime in the late years of the 19th century. If you want to put a date on it, you can say 1897. That is when J.J. Thomson put lots of gases into a nearly fully evacuated tube. And then this tube had two electrodes, a cathode and an anode, and then he applied a huge amount of voltage between them. And this is a very violent thing to do. And when he did it, he tore apart all these atoms, or a good fraction of these atoms. And as a result, he found that out of the dark, out of the cathode, came a lot of rays. And these rays, he demonstrated, were the same sort of rays no matter what atoms he put into the tube. And these rays had, these particles constituting these rays had a negative electrical charge, the same negative electrical charge, the same mass, and so on. So they were the same things. And what this showed also was that these things are actually constituents of all these atoms, and in fact it is believed now that they are constituents of all matter, or at least all atoms. Okay, so and this thing is now called an electron. Now, okay, the origin of this word is electricity and tron. I mean, electricity is amber. Of course, that has a historical background to it, that, amber in Greek. And, electricity was first produced, as you know, by rubbing amber against something else. And then the word tron was added to it, which means apparently in Greek the means by which it is done. And this word electron was first brought into use by an Irish physicist called Johnston Stoney in 1879. There is an interesting story about that also. You know, 1879 is a little bit before 1897. So you can ask, you know, how is it that the name was there but the thing was not there? Well, the thing was there but in a different form. Johnston Stoney actually came upon something which many other people had come upon, which is the following. You see, long back, even with respect to 1879, in the 1840s or so, Faraday did a lot of experiments on electrolysis, which really established the science of electrolysis, which started the science of electrolysis, and he found 3 regularities which are known as Faraday's laws of electrolysis. And he also found that if you apply a certain amount of voltage and you deposit in the cathode the equivalent, gram equivalent of a certain piece of matter, it always has the same charge, same electrical charge. So this was a little surprising, and he noted it. The Scottish physicist James Maxwell, he also noted it in his famous book on electricity and magnetism, and in a footnote he said that this implies that there is an atom of electricity, that you know, there is some discrete charge, and he even okay, you can even calculate the amount of okay, you can calculate the charge, yes, because you know the total charge of a gram equivalent, which is a farad, and then you divide by the number of atoms, you can find the charge. So you do that, and this was the route by which Johnston Stoney, who also liked this kind of approach, gave this atom of electricity a name called electron. So people began to be convinced sometime in the 1900s, well, sometimes later, that electrons constitute all matter. Well before this became a universal conviction or a general conviction, a man called Drude in 1900, essentially 3 years after the discovery of, not discovery, or at least the entry of the idea of electron into our consciousness, Drude proposed a very strange hypothesis. He proposed that the outer electrons of each atom in a solid form together an ideal gas of independent particles. You see, independent particles with gas, we know what it is, like air in this room. That consists of nitrogen and oxygen in some proportion, and we know that it's a gas, so we always say it's a gas. So he said, well, electrons in a solid also form that kind of a gas. Now that's a very bold thing to say, because you know, even if I draw a very bad picture of atoms in a solid like this, you can see that atoms are in touch with each other. They are very close to each other. So how is it that you can think of them as forming an ideal gas? Well, his argument was like this, that well, if atoms are in touch with each other, each electron is exposed to influences of other atoms. So it forgets its parental atom, it leaves home, and it wanders around throughout the solid. So if it wanders around throughout the solid, well then, okay, then you have a very dense collection of these objects which are wandering around the whole solid. But then the thing is, well, all right, what do you do with it? He said, all right, let us assume that it forms a perfect gas. Now, this is a very bold thing to say, because you believe that you must incorporate the actual effect of other atoms, effect of the electrons on each other, because electrons are charged objects, so they must repel each other, and they repel each other quite strongly. So electrons, the effect of electrons on each other, and see, now we know with hindsight that electrons are actually waves, and they obey the Pauli exclusion principle. So all these complications are. So if suppose somebody had at that time too many worries, he would not have said what Drude said. Just let me give an example. You see, if you take a typical solid like that, you ask what is the density of electrons, outer electrons, which are most likely to be exposed to the influence of other atoms. and therefore are most likely to be free and move around. Their number is about 10 to the 23 electrons per cubic centimeter. And this is 3 orders of magnitude higher than the number of air molecules in this room, for instance. So even though the density of these electrons is enormously higher, 3 orders of magnitude higher, he said, well, let us treat this collection of electrons as forming an ideal gas. Now, this very reckless assumption actually works. Okay, we can say many nice things, and people have been saying very nice things, sophisticated things over the last century. Okay, we can say that these are actually plane waves moving in different directions through the solid and not seeing each other, etc., etc. And it works. And what is the proof? Proof of the pudding is in the eating. Well, it works because, you know, the cell phone, I don't know, I heard some cell phone ringing. So the cell phones we all use, that is based on semiconductor electronics. And semiconductor electronics in turn is based on the idea that electrons are free particles. The personal computer and the laptop, they are all based on similar ideas. So you can call this quantum technology, and the story doesn't end. In the last decade, at least 2 different families of materials have been discovered, graphene and topological insulators. And here, well, we have a new kind of quantum physics operating, and maybe someday we will have a new kind of quantum technology based on this new kind of quantum physics. However, what I am going to talk about is, in this background of electrons, of free electrons as suggested by Drude, a class of systems which is increasingly larger, in which this paradigm breaks down qualitatively. In these systems, the electrons move from one end to the other, so they are metals, but they have to avoid each other very strongly. So the electrons in these systems, you cannot call them quite ideal or free, but they are moving. Okay, so how do we describe such systems? Well, I will do it first in a kind of a formal way, and then I will show some pictures which show that in reality these systems do have very unusual properties. So the fact is that electrons repel each other. Just the Coulomb interaction, Coulomb repulsion, electrostatic repulsion. This repulsion is of short range in real solids, because you see other electrons, the phrase we use is that the other electrons screen this repulsion. So if that is the case, you can make another very simplified model. This other very simplified model is that you imagine that this very large number of electrons is living on a lattice, and living on this lattice, they hop from one side of the lattice to another side, and the amplitude for hopping depends on the distance between these 2 sides. That's what I have shown here as I minus j. Very often, this is too complicated, because there are in a lattice there are lots of sides, and then if electron is hopping from here to there, some amplitude here to there with some other amplitude and so on, I have to remember infinite number of numbers, which I don't want. It so happens that you don't need to, and it is often enough to think of just one number, that is the that is the nearest neighbor hopping amplitude. That is the amplitude for an electron to hop from one place to its nearest neighbor site. That is just one number, t. So that characterizes the kinetic energy, because if it hops, it can hop to the next site, and then it can hop to the next site. So it can hop away, so it moves. So the size of t is a measure of the kinetic energy of the system. The repulsion, okay, now you say, well, electrons repel each other. That is what was in the back of my head. So you say that, well, this repulsion is short range. So how short range can it get? Well, if the two electrons are on the same side, they repel. If they are on different sides, they don't repel. So that is about as short as you can make it. So this is the size of repulsion when two electrons are on the same side. So this is a very simple model which was actually proposed by Hubbard, an English physicist in 1960s, and as a matter of fact, it so happens that a lot of effort has been spent on this model, but except perhaps in one dimension, it has not been solved. And of course, we don't know whether it is very interesting or not. Now, this model is characterized by one ratio, which is U by T. So it's a model, you can say two numbers, but actually one ratio. All right. So if this ratio is much less than 1, then the effect of this repulsion can be approximated by its average, because electrons are moving away very fast and then this repulsion is very small, so you just look at the average. On the other hand, if the opposite is true, that is, if the ratio is much larger than 1, then you see, if two electrons are on one particular place, then this electron has energy U. If there is only one electron in this place, it has energy 0. And then according to the Pauli exclusion principle, since the electrons have spin, so that is the only quantum number which is at a given site. So it can be, spin can be either up or down, and so there can be either one electron or two electrons, and so the energy can vary between 0 and U. Now this variation can be very large if U is very large. So it doesn't make any physical sense to just take that average, because the fate of the electron, the nature of its motion depends very much on whether another electron is there or not. It just wants to avoid those sites where an electron is already present. So all right, in that situation, what happens? Well, the simplest thing which happens is inertia. That is, electrons don't move. So you have, let us say, one electron per site. Each electron sits in its own site. It doesn't move. This electron sits here, this electron sits there, this electron sits there, and they know that if they move, then there is another electron already sitting there, and so there is an energy penalty U to pay, and they don't want to pay that energy penalty, so they stay there. So that is an electron solid. And it is actually an insulator. It's a new kind of insulator called a Mott insulator. Okay, the other possibility is the electrons move. But they move strongly avoiding each other. And then you see it's a metal. So that is a very difficult situation. Say, okay, this is the theory, but then the question is, okay, I mean, this is fine, this is what this model says things should be, but are there such things? So, well, that is what I want to say. I want to say emphatically that there are many such things, and many of the things we do, many of the things they do, we don't understand, and even our understanding of these things is going to be of very great significance. Okay, so let me give some examples of such systems. See, for example, if you take systems such as lanthanum cuprate or lanthanum cuprate doped with strontium, both of these contain this copper ion in a 2+ state, which has an electronic configuration 3d9,4sp2, which means for our purposes here that it has a d shell which in principle can accommodate 10 electrons, but at the present for copper 2+ accommodates 9 electrons, so 1 electron less, so it has an unfilled d shell. Now it turns out that, okay, this is the way I am talking about it, but it turns out that this doped, strontium doped lanthanum cuprate is a high temperature superconductor. What it means is that it superconducts at a temperature higher than anything previously known. All right, what was previously known? What was previously known was that more than half the half the metals in the periodic, elemental metals in the periodic table become superconducting. They become superconducting, however, at extremely low temperatures of the order of a few degrees above the absolute zero. And as a result, they are very interesting laboratory curiosities, because you have to have a laboratory in which you can go to a few degrees above absolute zero, and then you can check whether something is superconducting or not. Now, the highest superconducting, the temperature at which something superconducts, that is called the superconducting transition temperature. That was about 24 degrees Kelvin above the absolute zero till about 1986. In 1986, these two gentlemen, Bednarz and Muller, they discovered in a family very closely related to this, superconductivity at temperatures much higher than that, about 40 degrees above absolute zero. Now the world record for superconductivity in cuprates is about 140 degrees above absolute zero. Now, why is this important? It is important because, you see, the liquid air temperature is about 90 degrees or so above absolute zero. So, if by using liquid air, cooling something with liquid air, you can make it a superconductor, that means a very great thing. Why? Because liquid air is an industrial product. I mean, it is, I don't know whether in Madras, Chennai or not, but it is carried around in tankers. There are tankers which carry around liquid air. It costs about as much as milk. So lots of people can have liquid air. And so if you can cool something, make something superconducting with liquid air, well, one picturesque way of putting it is that superconductivity left the laboratory and entered the industry. Now, our dream, the dream of many people in this field is that we should make something which is a superconductor at room temperatures. So if it is a superconductor at room temperatures, it will leave the industry and enter the home. And it can be used for all kinds of purposes in a home. That has not happened yet. But anyway, these people discovered a family of systems, cuprates, which were superconductors at very high temperatures. High meaning that they were superconducting at liquid air temperatures. Now, then people began to do experiments on this system and to do theories, and the experimentalists found soon that this was qualitatively unlike any metal known to man. Well, that was a generation earlier, and a generation later, and about 200,000 papers later, we still don't quite understand what makes it superconducting. I know that if Bhaskaran is awake, he will be very upset with my saying this, but okay, many people feel that way, those who are interested in this subject. One fact is that this problem routinely figures as one of the major unsolved problems in physics. I'm not very upset about this because you see the original superconductivity that was discovered in 1911, and almost all the great physicists whose names we all know and revere, like Einstein, Bohr and so on, they tried their hand at solving the problem of superconductivity. They could not, and it was only in 1956, which is almost 50 years later, that a theory of superconductivity was possible. So I'm not saying that this will also need 50 years, but I'm saying that the time scales here are of that order. Okay. So all right. So why is this relevant? It is relevant because copper I mean, many people believe that the culprit in this phenomenon of high temperature superconductivity, as well as in the fact that this substance has properties qualitatively unlike that of any metal which we know. The culprit is copper, which is a transition metal ion with an unfilled d shell. There is a similar family of compounds which, for example, contain cerium. And cerium, the electronic configuration is 4f25sp2, 4f1. So there is one electron in the 4f configuration, 4f orbital. One example of this is cerium, rhodium, indium 5. This is a heavy fermion metal. Heavy meaning what? It's not heavy to weigh, but the effective mass of the electrons in these systems is about 1,000 electron masses. So this, okay, I mean, in some sense it is really very heavy. Now these systems, these cerium containing systems, they are not only very peculiar metals, but they also, many of them are nail antiferromagnets and superconductors and so on. So the simple belief then is that, okay, if you have systems which have, that is, if you have solid state systems or condensed matter systems in which the d and f shells, f orbital states are unfilled, then that may be the home of the strangeness of these systems. But actually that is not the case. You see, I mentioned here two examples. One is an organic compound which we write as BED, TT, TF, TC and Q, whose full form is this, which I don't want to pronounce. This thing has a metal insulator transition at 330 Kelvin. This metal insulator transition means something very strange also, that you see the electrons in this system below a certain temperature don't move, above a certain temperature move, and all together. So this generally doesn't happen. So that many people believe that that is because of strong correlation. That is the fact that electrons have a tendency, because of the strong local repulsions, to repulsion to stay wherever they are. So that is one example. Another example is C60 doped with potassium. This is not quite organic, but it's a superconductor at a very high temperature. So both of these, neither of these has a d or f electrons. They only have sp electrons in unfilled shells. So the conclusion I can draw is only this, that there are many systems which we actually don't recognize, which may be very strange, and the source of their strangeness may be that the electrons in those systems, they move, but in a way which is not like that of an ideal gas of electrons, and may be very strongly and qualitatively influenced by the fact that they are strongly correlated. Okay. So let me, that seems a little vague, but so let me say that there is one common strangeness, which is that in these systems there seems to exist a very low energy scale. This low energy scale is of the order of 2 to 600 degrees Kelvin. Above this energy scale, the thing is still a metal, but it's a kind of an incoherent metal. It's a bad metal. Below that, it's a coherent metal. Now, you see, why is this temperature scale unusual? It's unusual because, see, given the density of metallic electrons in them, we expect a scale of the order of 30,000 degrees Kelvin. So, nothing should happen at 200 degrees Kelvin or 300 degrees Kelvin, but it does. So, that may be the sort of defining feature of these systems. Okay, so let me give some pictures, show some pictures. You see, this shows the electrical resistivity of cerium aluminum 3 and cerium copper 6 as a function of temperature. Now, what are we supposed to note here? We are supposed to note here two facts. One is that the electrical resistivity vanishes at zero temperature of both of them. Now, that is good because, you see, electrical resistivity means resistivity to the flow of electrical current. Now, if you cool something, then all the disorder becomes less and less and less and less, and the thing is very cold. And if it is very cold, nothing should randomly affect the motion of electrons. And if that happens, then the electrical resistivity should go to 0, and that is exactly what happens here. The other interesting thing is that the electrical resistivity rapidly rises and attains some sort of a constant value at temperatures which are pretty low, like 50 degrees Kelvin or so, in this particular case. So it is, this kind of thing, having a non-zero value of resistivity which doesn't depend on temperature would be all right if temperature is irrelevant. I mean, if, for example, suppose the system was a collection of incoherent scatterers. I mean, the scatterer is located here, there, etc., completely randomly, and the electrons move through it and then will get scattered randomly, and so they get some resistivity, and this arrangement doesn't depend on temperature. So it becomes quite incoherent. I mean, that's one interpretation, that it becomes quite incoherent, but it becomes incoherent at a particularly low temperature. Okay, so there is a sort of an incoherent region, there is a coherent region, and there is a crossover temperature. Okay, so this is another example of the same thing. This is the optical conductivity of a cuprate, copper oxide. It is, in our language it is called bismuth 2212. Okay, what I have shown here is the optical conductivity as a function of frequency. Now, how do you measure optical conductivity? Well, I mean, you take a piece of this thing and then shine light on it. Some light is reflected, some light is transmitted, and then there are very complicated procedures through which from the fraction of reflected light or the fraction of transmitted light, you can finally infer what the conductivity is. It is the real part of the optical conductivity. So this is the real part of the conductivity as a function of frequency, and okay, let me go to the page I was talking about. Yeah, so all right, so this is the optical conductivity as a function of frequency. What we are supposed to note here again is the following fact, that at a particular doping x equal to 0.1 and different temperatures 50, 295, 500, forget this curve. So you look at, that is, it is the same compound. It is the same compound, which because the doping is the same, doping level is the same compound, just measurements done at different temperatures, 550 Kelvin, 295 Kelvin, 500 Kelvin. And look at what happens. At 50 Kelvin, the conductivity is pretty large, and then suddenly it becomes small, and then it continues to be small. At 295 Kelvin, okay, it is not that large, and then it becomes small again. And the conductivity here is exactly the same at all these temperatures. But what happens here at very low frequencies does depend on temperature. And the temperature scale on which it depends on temperature is very low, like 200, 300 degrees Kelvin. These spikes which distract our attention, they are due to absorption of light by lattice vibrations or phonons. Okay, this is another example of the same thing. You see, this is the thermopower as a function of temperature of a compound NaXCOO2, that is sodium cobaltite. Now, there are several curves. These curves correspond to different values of doping. Unfortunately, I don't remember, that is, there is a connection between X and this number, but I don't remember that connection. But the thing we are supposed to notice again here is that, look, the thermopower rises linearly with temperature. We have been told that if you have a degenerate Fermi system, the thermopower, which is due to the entropy carried by the charged objects, which is electrons, this thermopower will be proportional to temperature, because in a degenerate Fermi system there is hardly much entropy. It's highly ordered. I mean, just some electrons, the Fermi energy are excited. So that is why it is proportional to temperature. But suppose it were a completely non-degenerate system. You know, electrons are like dots sitting there, and they are moving around, and they are carrying current, electrical current. You know, as they move, they, you know, there is a flow of entropy, and so there is a thermopower. And you know, if they are classical objects, there will be some number which will characterize the thermopower. So that is what is happening in this systems. You see, it is as if it was a degenerate system, but as if the temperature at which it became non-degenerate is about 100 degrees or so. So above this very low temperature, it behaves as a some kind of a classical or incoherent system. So let me just go through these again. You see, these there are three different measurements for three different families of systems. They all show that there is a very low coherence temperature, an unexpectedly low coherence temperature. All of them involve one important constituent which has either an unfilled F shell or an unfilled D shell. Okay, now of course we have like all theorists, we have been interested in this, and we have been trying to do something, and we have a schematic picture of how this can happen and so on. We have some SU2 cross U and lattice gauge theory. If you have it in the classical limit, it gives you this incoherent Fermi liquid, and in the and then it crosses over smoothly into this coherent regime due to quantum fluctuations, and this occurs at a temperature T star, which can be shown in some cases to be rather low. And then when it becomes, when quantum fluctuations are dominant, then it can even become a superconductor and so on. So all the differences reside here, and the commonality resides there in the coherent systems, in strongly correlated systems, and the crossover takes place at an unusually low temperature. Okay, so let me summarize what I have been trying to say. It is this, that many independent electrons together, they have been experimentally and theoretically explored for more than 100 years. And even today, we are finding that they do unexpected things. And two examples I mentioned, which I mentioned here, are graphene and topological insulators. Now, many electrons strongly avoiding each other lead to very strange behavior, which has been explored increasingly in the last 3 decades or so. Unfortunately, we don't have a single paradigm which is like the Drude paradigm for these systems. So this is, I think, a very significant problem in quantum condensed matter physics. So, you know, there is a great deal of ferment. It's not as if, you know, this is a new thing. I mean, people have been worrying about this for a long time. Lots of very powerful physicists have been worrying about this for a long time, but we don't have a new paradigm. So are we on the verge of a new paradigm? And the real question is, do we need a new paradigm? Because many people feel that, oh, you know, what we have is enough. You just, you know, dress it up with something or the other, and then you can make sense of what is going on. So, okay, I mean, there are many views on it. Anderson, who is perhaps the greatest condensed matter physicist of the second half of the 20th century, he says that this is actually a log jam in condensed matter physics. See, it is like this, that, you know, a log jam, when does it happen? You know, there is a river, and you know, there are big trees. You don't want to carry them around. You just want to cut the trees in the forest in which that river is, and then float the tree, the cut tree. But then suppose the rate at which you cut trees becomes very large, then there is a log jam. There is no flow. So that is perhaps what is happening. In a very general sense, I would say that we have not been able to think properly about these things, and that is what this, these lines from Tagore say, that you know, it is possible that in the dreary desert sands of dead habit of a free electron theory, the clear stream of reason has lost its way. So I really do not know. But then, you know, you may ask, no, why bother? You know, maybe one day we will understand what is going on. We will have a new paradigm which will be natural for such strongly correlated electron systems. So what? I mean, okay, some physicists will be happy. So I mean, the world is not made for making some physicists happy. So okay, it will give us a new language which some books of nature are written, etc., etc. But the thing, you see, unfortunately, we live in an increasingly technological age, and it turns out that the solution to this problem is actually pressing upon us. And this is what I want to mention in my last slide, that it may help us do new things and understand pressing as well as connected mysteries of great technological moment. And this is the new science of oxide interfaces. So now, I mean, this is something which is just beginning. So I'll just conclude with showing a very fuzzy slide. You see, this is a conference held in England a few months back on the new science of oxide interfaces. And this is the frontispiece of the Philosophical Transactions of the Royal Society, in which lots of articles on the subject are put together. Now, what this picture shows is the following. On this side, you have strontium titanate. So at the atomic level, strontium titanate sort of pictorially looks like this. Some octahedra which share corners with little atoms here, which may be the titanium atoms in this particular case. Okay. Or strontium atoms in this case, yes. So now the excitement is the following. About 6 years ago, some physicists, Huang and others, they put together layers with a particular crystallographic orientation, 001 orientation, of strontium titanate, which is at the bottom. This is at the bottom, and lanthanum aluminate, which is at the top. And this is not a trivial thing, because to put together atomically perfect layers of transition metal oxides has taken this long. It's a very difficult enterprise. So they did that, and they found something very bizarre. What they found was that if the number of lanthanum aluminate layers is 4 or more, number of top layers is 4 or more, the interface is metallic. If it is less than 4, the interface is insulating. Now this is interesting because the parent compounds in the bulk, both of them are insulators. So it is funny that you see, you take two insulators, put them together, and the interface becomes metallic. Now, why is this interesting from a technological point of view? Because much of semiconductor electronics today depends on interfaces, the properties of interfaces. So, if you can make new kinds of interfaces, then you have a new kind of electronics. And you see, these systems, they are, in this particular case, they are transition metal oxides. One of them is D0 configuration, this one. And so you can make many such interfaces. And the bulk behavior of these systems is itself not understood. I mean, these transition metal oxides, they are believed to be, the electrons in them are believed to be strongly correlated. And it is believed, I mean, it is known that they give rise to very strange properties, both in the so-called normal or metallic state, superconductivity. They have high degree of superconductivity, new kind of, multiferroics, ferromagnetism, ferroelectricity, all kinds of things happen in such systems. So, if the bulk itself is so rich, then you may ask the following question. You see, if the bulk is so rich, then you may wonder, what will the interface be like? And we don't know. We don't know what kinds of things the interfaces will bring us. But this is a very, I would say it's a very pressing question, because this may give rise to, you see, we may be watching the birth of oxide electronics. We may be watching the birth of a new family of electronically significant systems. I mean, systems which can be significant for making electronic devices, which are qualitatively different from semiconductor systems, which are the devices which drive today's electronics. Of course, you may ask, why do we need new electronics? That's another interesting question. But for the technologically minded, this is a whole new world. And this new world has already come, you see, in 2006. I must tell you also that people are still quarreling about why this happens. Because this interface is not only metallic, it is ferromagnetic, it is also superconducting. So the origin of all these strange properties is not very clear. So I believe that both from the point of view of fundamental understanding of a large number of electrons when they are very close to each other, and the possibility of applications of this understanding or applications of such systems to new devices, we are at a very interesting threshold. So the next 50 years ought to be very interesting. Thank you very much.
Questions?
I would like to know the exchange correlation schemes that have been used so far earlier for the conventional systems and strongly correlated schemes. There should be some connection between these two. Or in other words, I would say the BCS theory, which is applicable up to 23.2. We cannot have a cutoff line for the conventional superconductors and the high TC oxides. There should be a single unified theory. So, or otherwise the strongly correlation and the weakly correlated systems also should be merging with each other.
Yeah. I mean, about the first question, there are lots of efforts people are making towards marrying density functional theory, which is one way in which electronic structure of many conventional systems is determined, with strong correlations. And these things, these attempts go by the names of DFT plus DMFT or DFT plus U and so on. So I mean, those things are getting very strong, and so people are doing that. About the question of whether BCS theory can usefully and meaningfully describe these new superconductors, I think we don't know. And I will give you a very simple example. You see, we all believe that we know ferromagnetism or antiferromagnetism. Okay, I mean, if we talk about such things, we use some Heisenberg model, nearest neighbor exchange. So in this, what are we doing here? You see, we are assuming that there are spins and that they interact. We don't ask when do this, at what temperatures do these spins form. We assume that these spins are God-given and that they interact, and their interaction is what leads to long-range order, broken symmetry, new excitations, Goldstone modes, etc., etc., etc. But in the BCS theory, you are assuming that the formation of the spin-like object and its long-range order occur at exactly the same temperature. So from this point of view, you may say that BCS theory is somewhat of an aberration. But I mean, I also was brought up on BCS theory, but
you said oxide electronics would be richer than semiconductor electronics. Will there be a kind of, in fact, if oxide electronics comes, will there be any revolution in the field of devices, electronic devices?
I don't know.
Will it get into the domain of nanotechnology?
That also I don't know, but